So
Okay.
let's start the recording. Do you all have access to the lab on Moodle?
I think yes.
Okay, that's pretty nice. Let me start sharing the screen. So this week's lab is going to be a little bit heavy on content, but we're going to skim through it extremely fast, right? We're not going to go into too much detail about every single thing. The majority of this code is basically just pure Python, so you're already familiar with everything that you're seeing here. The only differences will be just the parts that we will be adding, things like how to interpret, how to look at these charts, what to understand from these charts, stuff like that, right? But the rest of it, the majority of these code, you're already familiar with it. If, for example, this case, when I used to teach this course for master's students, they already did a natural language processing course before it. So they already were familiar with concepts like these vectorizers, TF, IDF vectorizer. Let me just check where it is. Where it is. Should be somewhere here. Here. So yeah, the TF IDF vectorizer, so as easy for you guys to follow through. So we will try to go through them in like a very easy manner. If you need like into detail about what TF IDF vectorizer is and how it is used for natural, just a text classifier basically, we could do that, but hopefully
Nice.
Я как понял, если добавляется у него коллап в его связь, то это все, короче. Это все падает.
sorry guys, my internet connection is actually very horrible because of these restrictions. So it might happen again if like I drop like this pretty awkwardly, right? So yeah, sorry in advance, right? Yeah, for this week's lecture or for this week's labs, we're going to go through the following. The first one is we will introduce the library called Interpret by Microsoft. It's actually quite an amazing library, so it could be considered as a replacement for sklearn for things which are, so for things like things about interpretability in general, or even like building your model from scratch in a way that is extremely interpretable. And then, of course, we will talk about the two topics that we have seen during today, the last lecture, which is Lime and GradCam. Hopefully, you will see, or you will start to appreciate a little bit why PyTorch was very big success in the research field, and how did it really completely change the game in deep learning, especially when compared to TensorFlow, which is an extremely rigid framework. So yeah, the library is pretty easy to install, especially on what is it called, on Colab. We'll try to run it, but in case things don't work very well because of the internet, then I will just continue presenting it directly. What we will do is we will get two simple data sets, one for classification and one for regression. These data sets are extremely basic. So this one, for example, it's an adult data set. And basically what it does is the following. Let's just look at the data frame here. So we get information about for things like the age, working class, I don't know what this is, education number, marital status, whether they are married or not, occupation, relationship, race, gender, capital gain, capital loss, hours per week of work, of course, native country, and the majority of them are the United States with few exceptions, and basically the income, whether they make above 50K or under 50K. So it's a very simple classification task, a beautiful data set that you could find in any example, right? Whenever you're working with tabular data sets, you're going to find features like this, with some of them being numeric, some of them being things like this, which are categorical, some of them are nominal. So it's pretty much the standard, your standard data set. Usually before you go and start actually working with the data that you have, you would want to understand the data, understand the relationships between the inputs and the predicted variable, right? And for that, we have luckily something pretty easy, which is class histogram.explain data, already provided by, what is it called, by Interpret by Microsoft. And it already provides you with this beautiful charts that explain to you things like, here, for example, in our data set, we can see that there is a slight data imbalance. It's not a drastic data imbalance. Usually whenever we speak about a major data imbalance, one class is like 100 times bigger than the other class. But in this case, they are 10 times. Okay, so it's how much? 19K, and this is 1.6K. So it's more than 10 times, which is honestly not that horrible, right? I think this is 6,000. Oh, yeah, this is 6,000. So 6,000 with 19,000 is like 3 times bigger. Not that big of a deal. So it's not a huge class imbalance that could ruin our model. And then it goes through even more interpretability or more understanding of your data. So you would here see where the distribution of your data lies. These concepts are extremely important, as we said, for the monitoring stage of your product. Once you deploy your model and you understand that your model has been trained, it's good, it works very well, and the business has started using it, you need to verify that your distributions remain as similar to the training part as possible. So here, for example, we see that the majority of our data lies here, right? So this is the majority of our data. If, for example, during inference or during deployment, you start seeing that the majority of the data you are receiving is on here, on this side, with this kind of distribution, you will immediately find out your model is useless. Your model is trash, needs to be trained again from scratch. So such concepts, as you can see, it's pretty easy to do, very easy to check. Sorry. Is my internet still horrible? Can you guys still hear me well?
Yeah, but we can't hear you partially sometimes.
Oh, that's horrible. That's awful. Let me try this. We can hear, but with lag. Okay. That's the problem when I'm doing also with VPN. I hope it improves hopefully over the next week, because they will close these internet restrictions. But yeah, let's just do our best and we continue. So you also can see the same things with when it comes to, you know, other categorical features. Here, for example, it tells you how many unique features do you have and the distribution of these features across, or the data across these features, and the distribution of the classes across these features. So here you can see that the majority of the people that you're working with are private sector. So they're not self-employed or working for the government or local or federal government. This is specific for the United States. But for example, here without pay, you don't, I think you have just like one or few samples, something that you immediately should be dropping. Here, this is also, again, the same things, education, you've got some college, professional school, preschool, master's, high school degree, doctorate, bachelor's, associate, and I don't know what these are, right? These are just like high school levels. So here you can see that for the majority of the cases, if you have, a master's degree or a bachelor's degree, your probability of being paid above 50K a year increases drastically compared to somebody, for example, with only a high school diploma. And same thing between a bachelor's and a master's. So here we can see that the majority, we have more bachelors available, but the distribution in here is telling us that if you are a bachelor, you are more likely to get below, 50K, whereas you are compared to, for example, somebody who's a master's student where it's, more of a 60-50%. And then if you go to a PhD, then you increase the likelihood that you will be paid above 50K even higher, right? So these are some interesting, insights: educational number, marital status. Yeah, divorced. Yeah, don't get divorced, guys. And here, what do we have? Occupation, exec, craft repair. What is this? Exec and managerial. So they are more likely to get to get more than 50K when you go to management. Professional specialty, I don't know what this is. Sales is also pretty interesting. So these are pretty interesting remarks that you could get very quickly by looking at the data like this. And you can see in here that the majority of the people that you have are working around 40 hours a week, which is the typical thing that you would imagine in a just a normal job. Anybody who's working above, usually either you are here, for example, a doctor, like medical doctor who works a little bit more hours and get paid even more. If you are getting paid even less, then in most cases you're part-time. And here, this is a great opportunity for you to actually build new features. So doing some feature engineering. This is why these steps are very important. So hours per week is a very, what is it called? Is a numerical feature. For your model, if you are, for example, working with a decision tree or something like that, it's very important to include as many new features as possible, which are preferably categorical features. So here, for example, what we can see that this category, let's call them part-time workers. These are part-time workers. And for the majority of the cases, sorry, I don't know how to turn this off. I honestly have no idea how to turn this off. Let's just keep it. So yeah, so we can see that, for example, for this part, these are part-time workers, and the majority of them, they never earn more than 50K a month. So or a year, sorry. So it's very interesting to just add an extra feature in here that will help your model immediately eliminate the majority of the cases and make your decision tree even more cleaner, shorter, and more generalizable for future cases. Same thing, for example, in here, you could say that this is typical work week environment. So this is typical full-time. And these are people who work overtime. And usually these are either people who are independent contractors, or they work for themselves, or specific case, right? Or specific category. This already helps you build kind of like 3 big parts of your tree that are very humanly interpretable if you start building, these human features or humanly understandable features. Same thing for the others. Continue looking through them and try to understand what is happening here. So for example, you can clearly see that your data is only about the United States information. So most likely for these models, for these countries, you should absolutely not be putting your or deploying your model in these countries, because you have absolutely no data about these countries. Things like marital status, for example, in the United States, and after you get a divorce or you never be married or stuff like that. So these are situations which are different country to country, and generalizing from the US to, for example, to Algeria or to Saudi Arabia is absolutely not something that the model is going to be able to do. After that, we reach the actual, building of the classifiers. The good thing is Interpret comes with similar models to sklearn. Everything you see in sklearn, you can find it here as an explainable model. So here it has its own logistic regression. It is trained in the same manner. You have the same, same things of, I don't know. Yeah, so it is currently a wrapper around linear models in sklearn, right? So as you can see, it's already based around the sklearn model. It just provides a little bit more functionality in terms of interpretability. That's all it does. So classification tree, also the same thing. It just goes to the decision tree of sklearn and provides some ability to do the classification tree with the shallow depth. Decision list classifier, and then we've got here explainable boosting classifier. So here you can see that you could just train these models, instantiate them with a random seed. The random seed here is just something that allows us to do comparable results across different iterations, so that my results are the same as your results whenever you are running a code on your side. So it's completely useless, no need to worry about it. Here you can see the same thing, EBM.fit xtrain ytrain, just like any other model out there on, for example, sklearn or something like that. So let's try to run this code and see how it goes. Downloaded the data set, all good, all good. Here it reloaded this one. It's gonna take some time, as we said, because of the internet, which is pretty sad. And there we go. We train our boosting classifier, and then we explain it. And here you can see the same things as we did before. So you have local explainability and global explainability. So you will be able to perform both or all types of, what are they called? Explainable scope or interpretability scopes through this. Let's just keep waiting for it to train. It should not be super slow. I think I have, yeah, I do have Colab Pro, so it should be good. Let's see. Okay. Hopefully, once it finishes the training, we will actually see what global explainability looks like. But again, it's going to be a lot about these kinds of charts, things about like the error, how it is being distributed across different categories in specific features. You will be able to understand literally everything about your model and hopefully provide global insights about the model. And from this, you can see, for example, we're taking just 5 test instances and we're trying the local explainability on them. So here, it's not the local explainability for a group of features, but more like local explainability for 5 different instances, right? So we will see it together. Let's see it together, right? Here. So here, for example, you can just see individually, each one of these 5 cases, it tells you what the actual class is, what the predicted class was for that model. This was the probability. So you can see that the model was actually extremely sure about it. And here you can see things like the intercept. Intercept, as you can see, it's extremely negative. Why? Because we do actually have a big data class imbalance. So here you can see the response distribution. We have a major difference between the category distributions, and that is here justified with the intercept always being a very important feature. In a negative way, right? So if it was, for example, the people who are earning above 50K are more likely to exist in our data, then you would see that the intercept is a positive number. Whereas in this case, as you can see, it's a negative number because we are more likely to be on the 0 class than the positive class. And here we can see education. He has in the 7th or 8th grade, clearly not something that is helping him at all. Occupation, other services, so we don't have enough information. Education number, gender, female, sadly, you know, females earn sadly less, especially when they get married. So here we can clearly see that just because of being a gender female, you are more likely to be losing money. And we can see also that in the what is it called? In here in the data. Let's see, occupation, relation, gender here. So yeah. You see the distribution of male workers is even higher than those of female workers. And even within the male workers, you can see that there's a higher percent or higher likelihood of being a top earner than when it is for being female, right? And we can see also maybe the same things, for example, in the race. So white people have this big gap of earning above than 50K. compared to, let's say, somebody who is black, where the percentages are definitely not in your favor, or somebody who is, Eskimo or from, Asian Pacific Islander, or an other, sadly, they are all, in a very bad situation. And this can already help you understand what are the features which are extremely important for the classification. So for example, if you come to your data and you see something like gender, let's go back to gender. Sorry. Opa. So if you go back here, for example, to gender, and for some reason you would see that gender has exactly this shape here and the same one here with the same distributions and everything, then here you can clearly see that gender is not an important feature because it's not discriminative. It does not separate the data into two categories. Whereas here we can clearly see that gender was pretty important for us. Working, self-employed, not Inc. I don't know what this not Inc. is, but probably it's a bad thing. Here the age was 62, so she's a pretty old person. And usually old people tend to earn higher than, say, for example, somebody who's in their 20s. And let's go capital gain, I don't know, relationship, not in family. So not in family, for example, here was a bad thing. Widowed, marital status is widowed, so that's usually a good thing for women. So if your husband has died, at least probably he would have left you some, some income, that disposable income that you could use. Relationship and hours per week. I don't know what that even means. And here, age and relationship. Oh yeah, this is just a combination of these features. Okay, age and relationship. So that's pretty good. Let's go to someone who is like a positive, actual positive and predicted positive. And we can see in here the capital gain is like ginormous. So probably he makes a lot of money, this person. Age is 25. Wow, he's a young person and he makes a lot of money. That's nice. He has never been married. He works 50 hours a week. So that's a good thing. Let's see the education background, education, where it is, education, bachelor's. So this is a bachelor's person and he makes a lot of money. See, that's good. This is what we were discussing about when we said local explainability. So you are explaining to your clients why, for example, you refused their loan, or why did you not why did you accept. Usually if you accept, they're pretty happy and they're not going to ask questions. But if you say something like we don't or say no, you should at least provide some answers. And here, for example, we have the third level of or the third scope of interpretability, which is the feature importance, or the importance of the individual parts of the model on the actual final prediction. And overall, we can see things like age, marital status, capital gain, relationship, occupation and education number, gender, hours worked per week, and education are extremely important for the model. Things, I don't know, like race, because we had only almost one race, right? So everybody was almost white there. Here, this one was not important. Native country was also not important, mainly because we only had one class, which is the United States. So these features, you could safely drop them from your model and keep only these features in your model for the sake of having a greater generalization. And here you can see the distribution of your error across your data. So this allows you to understand what these features are contributing to your model's results and to the model's error or to your model's performances, right? So this allows you to have extreme in-depth information about which features you're able to provide good results for and which features you should probably not work with. So for example, if you see that for the category, I don't know, or for some country, because we've seen that country is not something that is extremely important. For some country like France, where you don't have enough data, you will probably see that it has a lot of error. So preferably do not deploy your model for that specific category. So this is what you get from the models. And here you could build other types of models or other types of explainability. And this is the explainability of performances. So here, let's take a look at this, for example. And here you can see the ROI curve, ROC curve, sorry. ROI curves are something else. So here you can see that are the ROC curves. You can see the area under the curve. And this allows you to, again, simple understanding of what your model is doing. Here you could, I think this is just going to be the same thing. If I'm not mistaken, train test split. This is for logistic regression. And then we will do exactly the same things. Here is decision trees. We will do the same things, and then it just shows everything. So for the sake of saving a little bit on the internet, you guys could launch this and see, for example, the differences between, or let's just launch one. So this is the AUC, sorry. It's 92%. Let's go to something like logistic regression just to see the actual drop in performances. This could be like interesting for people to see. Let's look at it. So first of all, they are much faster than the boosting model. And we can see that logistic regression, for example, is a little bit less performant than the other one. Me personally, if I see that the drop in performances is very small, I would manually try to improve the logistic regression model rather than use the explainable boosting model. Here we see the classification tree was just horrible. Your data is just not perfect for this type of models. And we see that the boosting is the best model. Here, for example, for the, sorry. Oh, how can I find it again now? Yep. So here you can see things like the actual decision tree, and you see how it works. This is the linear regressions coefficients. So this is also interpretable. Let's me just try to get back that graph. I lost it. This is why it's hard to use a little bit. Let me just try maybe to find it here. Yeah, the good thing also about this one is it provides a very beautiful and real-time dashboard. So in Colab, it's not going to work, but if you run this code on your local machine, you're going to be able to get like a new kind of website that opens up, and it will have all of these drawings or all of these, what are they called? All of these tables. They're pretty fast to load, and they work pretty well. And here you will see, what are they called? Black box models. These black box models are exactly the same thing, but what we'll be doing is we will apply PCA. I'm not going to be explaining what PCA is. I'm hoping that the majority of you already have done this with Professor Khan. Is that the case?
Yes.
Yes. So just a quick recap, PCA will just basically destroy all the features that you have and convert them into something a little bit smaller and more impact. So it will just like compact those features. And we're not going to be using PCA because we want to reduce the size or anything. We just want to use it so that we make sure that whatever model we will be using has no idea what the actual input features are, right? So it's kind of a black box that is, we have no idea what it is. We have no way of interpreting its actual results, right? So for example, for something like linear regression, we can just look at the coefficients and understand that something like age is very important because it has a high coefficient. But when you apply PCA and perform whatever model you want to perform, it will be very hard for you to actually do that third level of explainability, which is, or interpretability, or third scope of interpretability, which is the ability to understand how each different part of the model affect the final prediction, right? So here we will be exactly doing the exact same thing, but instead of doing a more in-depth or more, how do we say this? Yeah, white box or glass box, sometimes people call it interpretability, where your interpretability model is part of the, what is it called, of the model itself. So your model is extremely interpretable. Here you could replace, for example, a random forest with a neural network, which is extremely hard to interpret, and still get the same results as we have seen before. But instead of getting them through something like the actual model itself is interpretable, now you are getting them through what we have seen in class, some things like LIME for tabular data sets. And here you can perform your local interpretability using LIME. LIME is not the best thing as we have seen yesterday because it's very slow and it provides very, let's say, biased information because it's extremely local, where compared to something that is by default an interpretable model. but at least it is better than nothing. At least it gives you the ability to see what is happening inside your model. It's better, yeah, as we said, it is better than nothing, right? And then we have another one, which is more sensitivity, and it allows you to understand the importance of your features. So this is going to be allowing you to understand the sensitivity of your model with regards to your features, or the importance of the features with regards to the prediction. So this one should be able to provide you with that third level of interpretability. We could take a look at them super quickly. Sadly, they are extremely slow to run, but let's try. Okay, I think they moved the data set. Okay, so they moved the data set from here. Has been removed from scikit-learns. The Boston housing prices data set has ethical problems as investigated. So yeah, they have investigated this feature and this data set, and they decided to remove it. Let's go back with the same original data set like this one. Should be good for us. And let's just remove this data set from here. Let's go down, 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 down. Yep. We're not going to do this. 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 And we're not going to do these. So we're going to keep the same X train, Y train as the previous example. Sorry. Let's run again. This one is not going to do anything. So it disappears, the error. And now let's run. Oh, yeah. So we're using a random forest classifier. Let's not use a random forest classifier. Let's use something. And we're using PCA also. What we had. So working class was categorical. Let's remove it. We have education, which is also categorical. Let's remove it. Education number. It's good. This one is good. Marital status, occupation, and relationship, race, gender. We also remove them. Preferably do not remove them. Of course, as you can imagine, you should do some encoding to them. But for the sake of just showing you guys the results, we're going to be doing it like this. Hours per week, we will keep it. Native country, we will remove it. Income, we keep it as it is the actual response. Capital loss, capital gain. So this is good for us. This is a good start. Let's go. Let's try. Something here doesn't work. Length mismatch. Oh, yep. So we're going to do the following like this. Keep it like this. And then what we will do is data frame is equal to data frame at the following. And let's remove what we just said we will remove. So education, work class, gender, all of these, we remove them, and we said native country. Let's run again. This should be fast. Okay, so it works. Well, let me just confirm that it has no categorical features. For the PCA, all is good. Yes. Let's go back to PCA and perform PCA. So here we can see that it should work. Right now, it is training. By the way, this is something that is extremely common to do, this pipeline situation, as you can see in here. So here you have PCA. This is your actual model. You have PCA followed by a random forest. This is something extremely common to do, especially if you're working with natural language processing. They said it quickly that it better to use interpret library instead of scikit-learn to train our models, since it will be easier for us to interpret. Yes, yes, absolutely. So if you are building a model that is extremely important for it to use something like interpretability and to have this functionality of fast interpretability, because these all these libraries or all of these algorithms are extremely fast to run. So even if you will try to build them yourself, you're not going to be able to match their speed unless you have like an extreme amount of workers working with you. So preferably always use the interpret from Microsoft library instead of sklearn. It has exactly the same functionalities for some specific things. For example, as you might have seen, train test split. Yeah, this is not something that is specific to interpretability, So you're definitely going to be using sklearn for it. But anything that is related to explainability, even things like metrics and evaluation, even things like that, preferably use this, right? Because instead of using just basic accuracy or something like that, here you're able to go much more in depth, and you can even go look at the accuracy across different categories or across different features and yeah, these variables, right? So it's much preferable to use this one instead of using just basic sklearn. So here we can see the accuracy. It's much lower than the 93 that we had earlier, mainly because we removed a lot of important features such as gender and occupation and just a lot of stuff that we removed, right? So here we have an error. The model, why is it not getting the model? Okay, so it changed a little bit. Let's get it here. Okay, and you can see that even for a black box model means something that you have no idea what it is, something that is so complicated like a neural network, you're still able to understand why did the model make its decisions. And here you can go for the same thing here. Let's just replace this with model and go. And this is what we call the Morris sensitivity. Sadly, since we completely removed the majority of the features that are actually important, Morris sensitivity is not going to be extremely high. But later on, if you bring back features like gender and stuff like that as just encoded features, you should be able to see in here much more, information about the different features, which features are important for the model, which features are not important for the model. So for example, here, capital gain is of course a very important feature to have. Same thing you should be able to get from partial dependence. Let's try it out. Should be quite fast. Let's see. Well, it was not quite fast. And just for the sake of going to the next steps, so here in the code, you will see the exact same thing instead of for something like classification, you will be doing it for regression. Sadly, we're not going to have enough time to basically go through all of these examples for the regression. It's the exact same steps. So things like glass box interpretation and black box interpretation. So things, as we said, models which are by default interpretable. Let me look at, so explainable boosting regressor, linear regression, or regression tree. So all of these are by default extremely explainable. Sorry. And then we go through the black box regressors, which are by default, as we said, not explainable. And here what we're using is the sklearn model followed by PC, or before that we use PCA to make sure that it doesn't even know what features it's getting. We finish the training. We do the exact same interpretations of the performances of the local level and of the global level using something like Morris sensitivity, which explains hopefully for us some global level information, especially the third scope of interpretability. As you can see, for models which are extremely complicated, there is no such thing as this is the third level of interpretability. There are different algorithms that you could use to get that third level of interpretability or that third scope of interpretability for models which you don't know. So there are algorithms, but each algorithm comes with a couple of what are they called? Sidebacks or bad negative stuff that come with it, right? So they just are not perfect, but they are much better than nothing. Same thing, for example, with Lime, right? So Lime, it's very slow, it is very localized, it works at the instance level, and it requires to train a lot of models for each instance, right? So that makes it extremely slow to work with, but it is better than nothing. If you have no access, you should at least have this working for you. So this is it mainly for tabular data. As we have seen, there are so many things that you could do. It allows you to basically first understand your data, understand what features you could include. So we have seen, for example, like something like working hours, where you could include other things like, is this somebody who was working part-time, which is most likely he's not going to be earning more than 50K? Or is this something who's working the normal, full-time job? Or is this somebody who is a bit more executive? So somebody who is more working, I don't know, like a big high-level manager who has to travel all the time, or maybe a doctor who is working 60, 70 hours a week because basically there's just not enough doctors in the hospital. So these extra features that you could include from looking at the data, looking at the distributions, are extremely important for your model's performances. So this is definitely something that I highly recommend always doing to increase the performances. So before you think about improving or changing the model, or going from a logistic regression, as you have seen, logistic regression was able to give us 90-something%, and the boosting model was able to give us around 93%. So instead of going with the boosting model, I would highly recommend going with logistic regression and adding some feature engineering to make the logistic regression more powerful. So here what we will do is now, let's just check. Do you guys have any questions so far about tabular data? How to interpret tabular data? So things like interpretable models, models which are not interpretable for both classification and for regression. What does it mean to have the third scope of interpretability? How can you perform the fourth scope of interpretability for a black box model? So for a glass box, so something that is interpretable, you're easily to do it, right? So you just look at the model itself and you can understand the features, how they're affecting the actual prediction. But for a black box, you are obliged to use something like Lime to basically provide that insight. And for also, again, for black box, to get that third level of, or that third scope of interpretability, which is how are these features important to the model, or how are these features affecting the final prediction? Then for these things too, you will also need an algorithm that does that. And we have seen 2 different algorithms that could provide some insight to that. Any questions about the lab so far? If there are none, then probably we just take a 5-minute break and we come back, we do Lime. After the 5-minute break, after the Lime, we take another 5-minute break and we do our GradCam. In GradCam, you will see the beauty, as we said, of PyTorch. And hopefully after that, we take a couple of minutes also for a break and we start discussing object detection. Let me pause the recording. And sadly, we forgot to continue the recording. So that was pretty bad. Any questions? Okay, seems good. So do you guys want to continue and finish GradCam and then take a long break and come back for the object detection lecture? Or do you want to take like 5 minutes break again, come back for GradCam and then take the long break? So Kareem has said yes, but yes to which option? The first one. So we continue with GradCam and we finish, take a longer break at the end. Okay, absolutely. Let's continue with GradCam. So again, for the GradCam code, you will see a lot of code also that I'm not going to explain, mainly because the GradCam code itself is actually, okay, so GradCam is a little bit long, but the majority of the code you're looking at, as we said, you are going to write it anyways, right? So the standardizations, all of these techniques, you're writing them anyways. Show camera on image, show camera on image, I don't know, show GradCam on image. So all of these things you're going to write anyways. The code that we will explain is the following. Here it is. Sorry. The GradCam code. That's it. It's big. It's a lot. It's a lot. I'm not saying it's nothing, but the majority of all of this code that you're looking at is something that you will be writing anyways for any project. So if you want to include GradCam, it should be just an extra file in your repository. Called it GradCam, and it just has one function call. You call the function, get the results immediately. Before we go into GradCam itself, let's start by appreciating a little bit PyTorch and why PyTorch is a very beautiful framework. So here we have this feature extractor class. It's going to be very helpful for us later on to extract the actual layers. So here you just give it a model, whatever target layer you want. So how do you get the target layers? I think here, let's go model. Let's go down. So let's say that you want this layer. You want layer 1. This is what interests you the most. So you just say, I want layer 1 as my target index, right? Or if you are working with numbers, you could just say layer number 45, and the model will understand which layer you're working with. So here, for example, here you have this layer number 32. This is the model that we are going to be working with. Let's look at it. And let's see what layer 32 is. Opa. So it is downloading. Here we go. So these are the layers that we have. We said layer 32, which is almost the final convolutional layer. It's not the final convolutional layer, but it's almost. So we could definitely go to 34 and get even better results from GradCam. After that, we have our classifier, which is basic. So here we are using 32. Let's go down a little bit. Yeah, where did it? Yeah, here we use 32 instead of 34. Let's go initially with 34, and then we go with something like 1 or 2 to see what the actual performance is or how the performances drop because of changing what layer we're interpreting the model at. So here, this is, as we said, just a function that goes through the actual model. And once it reaches the target layer, so it reaches the layer that we are interested in, what it does, it will just register basically the gradients and register the output of the model on those, what is it called? How do I say this? Yeah, the output of the model on that image, right? So what you will be doing is you will have image here. Here's image. You have layer 1, layer 2, layer 3, layer 4, layer 5, layer 6, layer 7, layer 8. In this code, what you're doing is you're no longer going through the whole model at the same time. You're going through the model layer by layer. So you go through the layer 1, get input becomes the output. Here you get the X, send it again and again and again until you reach your target layer. So for example, this is the target layer. We reach the target layer because it has the same name. What we will be doing in this step, we will just register the actual X. So we will save the X and we will register basically the gradients. At this layer, we will register the output X and the gradients at it. And from here, we will be able to later on perform all the activations or the calculations that we want. This is also another one that is another class that is going to help us. It's kind of a wrapper over the feature extractor. So it takes the model and the feature extractor, and it basically creates this target activation. Here you go, output. It changes the structure of the output, sends it through the classifier, and you get your model. Or so you get your results like here. And this one, it allows you to get access to the gradients pretty quickly, mainly because the self.extractor.gradients, they get calculated here. And then this is processing the image, useless. And then we go to GradCam. Here it's going to be pretty simple now that we have seen those two steps. Here it's going to be exactly what we have said in the lecture. So here, if you have CUDA, you will send the model to CUDA. If you don't, you don't. You have your extractor in here. You have the basic forward function, which is just forwarding the input through the model. And this is the call function. This is what what your actual code is, right? This is the GradCam being implemented here. So what you will do if you are in CUDA, you will send the input through CUDA, and then you call the extractor, and it gives you the features and the output. Here, this one tells you if you are working for a specific class. So you're trying to interpret, for example, class dog or class cat. If you're not interested in a specific class, then it will take the maximum class. It will explain the class with the highest probability score. Yeah, with the highest probability score. If you are interested in a specific class, you could just set the index to the index of that specific class. Basics. Here again, also very much basics. You will just be creating this one hot encoder value. We will see them later on during the code, but basically this is where you will have your actual gradients being averaged. Here, very simple, you will zero grad everything to make sure that absolutely nothing is affecting your calculations. As we said before, since we are here working with a simpler model, just a classifier and just a encoder and a classifier. So it's not really a dangerous situation. But if you are building anything that contains 2 or 3 different networks, always remember to, if you have an optimizer, set all of its gradients to 0. If you are not using an optimizer, go through the actual model and set its gradients to 0, just to make sure that nothing is influencing your gradients besides these actual weights or this actual calculation. Here, what we'll be doing is we will go through this one, GradCam, is the average of, this one is the weight. So this is the weight across the weights, which is the average of the gradients. Here is the gradients, extract, get gradients. What do we say this? You flatten them and then you send them through the CPU. You get the data, send it to NumPy, and here you have the gradients. Take the average or the mean across the basic, what is it called? The actual channels. And there you go, you get the weights, weight multiplied by the target. So the target is the actual, what is it called? A convolutional feature map. Let me just call it like this. This is the actual convolutional feature map. And this is the actual weights. And then you have here the function, as we said, pretty simple function. Cam is the average of, or the weighted average of the weight, which is the gradient or the mean of the gradients for that specific channel, multiplied by the channel. And then in here, what we are doing, as you can imagine in this setting, here, this is the ReLU. Remember, our last step was ReLU, and you could perform ReLU in a very simple way. You don't have to actually call the function. You just apply the maximum between the actual value and 0. So it basically removes all the negative values and keeps only the positive values, which is exactly what ReLU does. Here, this is a couple of resizements and making sure that the cam values are normalized. But other than that, you're good. This is an extra step, which is guided backpropagated ReLU. This is another algorithm similar to, what is it called? Similar to GradCam, but it's a bit better. We're not going to explain this one. This is just for people who want to do research on the field. At least you have it here ready and you could just compare between them. So now let's actually do GradCam. Start time. And time total is 2 seconds. And there you go. This is the image. Let me load it again. So GradCam took 2 seconds to run. And if I'm not mistaken, yes, so it took less than 2 seconds to run. Yeah, here we go. I don't know if this is 2 seconds or this is 11, 20. Yeah, this is 2 seconds. Yeah, this is 2 seconds and a half. Okay, so it was 2 seconds, not that bad. Whereas, for example, if we did, let's go back here to Lime and see how much time did it take. For the task with lots of features here. Let's try it. 4,000. Yeah, let's try this 4,000. It should give us the hours here, or the time on the left. Let's see. So it's so far, okay, it's very fast. So it took 7 seconds. Okay, yeah, the majority of the cases, you would have a lot more than 7 seconds. Let's see, here it should be like 2 minutes. Yeah, 7 seconds was actually not bad of a result. If you want to improve it, it could take around like 2 minutes or, well, it's fast. The GPU is pretty big, pretty good on here, right? Yeah, but that's the thing, right? So on the GPU, it's not that big of a deal to use Lime, mainly because here, as you can see, the RAM, we're started using it heavily, and we have a lot of RAM. We have 16 gigabytes of RAM, but it's not something that is extremely scalable, especially for like an industrial project. So if you are doing something for computer vision, always prefer to use GradCam over Lime. Although Lime is highly parallelizable and it works very well on GPUs. So as you saw, it takes like 7 seconds to actually get done. Here it took 2 seconds. So from 7 seconds to 2 seconds, it's not that big of a deal. But if you are working on a CPU, that difference is going to go from this one will become something around like 10 seconds or something like that to for Lime, it's going to be something around 3 to 5 to even 10 minutes. So it's definitely not extremely recommended to use Lime for images unless it is the only thing that you can do. And here we'll see GradCam's results. Clearly, GradCam's results are much better than the results of Lime, mainly because actually GradCam can tell you what the model is looking at. This is the actual thing that the model is looking at. This is not a guess or an educated guess about what the model is looking at. Like, for example, with Lime, because Lime is extremely dependent on the super resolution or super pixeling algorithm, which is something that is not learned. So this is something that is hard coded. It's just an algorithm, a greedy algorithm, very basic thing. So it's not something that you can trust for all types of data sets. Plus, you have the thing that is completely black box. So you have no idea if this is actually what the model was looking at. With GradCam, you are looking at exactly what the model is looking at. So this is what the model focuses on looking at, right? So this is it mainly for GradCam. There's lots of resources that you could take a look at and maybe get deeper information about what GradCam is, comparison in terms of speed, for example, GradCam versus Lime on different GPUs and on different CPUs. But just be extremely clear, GradCam is always faster than Lime. Always, no exceptions. Always GradCam is much faster than Lime. All good. Do you guys have any questions so far about today's lab? Seems good. So I guess that's it for today's lab. Let's take a 10 or 15 minutes break and come back for the object detection lecture. So the object detection lecture is going to be a little bit too long. We're not going to do it all today, so we're going to do only half of it today. So probably we're going to be finishing a little bit earlier, I think. How much time do we still have, by the way? When do we finish? Wow, we actually consumed all the 3 hours discussing the lab of interpretability. Oh, I did not expect that. I thought we only did 1 hour and a half. Wow. Okay. So I guess that means the object detection lecture is going to be done over the next week. So it's going to be done on the weekend, right? Why? How much time do we still have? Yeah, we still have 1 hour and a half. Okay, I did not guess that. So when did we start? Okay, good. So we're good, right? We still have 1 hour and a half. Okay, that's good. I did not. Okay, so this one is. Yep. This time thing is really not my strongest. Moscow time. So yeah, in Moscow it's 2:30. Okay, so yeah, we still have 1 hour and a half. You are absolutely correct. Yeah, we did not go overboard with this lecture, with this lab. Okay, then that's good news. Yeah, that was good news. So we'll take a 15 minutes break and come back and get the half of the object detection lecture done. Thanks, guys, for telling me. Okay, so this is 12:30, so we come back at 12:45, at 2:45. Yep, 2:45. 14:45. See you soon, guys. All right. So let's continue and let's get started with the next lecture about object detection. Okay, all good. Just a quick heads up, you should expect a new assignment, like the first homework coming soon on the Moodle. It's a very simple assignment. What you will be basically asked to do is go find a small data set, fine tune VGG 19 or ResNet 18 or something like that. And basically find specific situations where the model mispredicts or makes an error, and try to explain to us why did the model make that specific error. So the data set that you should find should be like something easy, something handleable on Colab. You train your model, use GradCam to explain the model's results, and compare both GradCam versus Lime to see which one is better at explaining the model's errors, or why did the model make a certain error. All good. Yeah. Let's start object detection lecture. No. Yeah, let me post it also. I think I should post it. Yeah, let's post the lecture first on Moodle so that we don't forget it. Here we get object detection. And let's first just, as usual, we will put the Canva link, lecture slides. And hopefully, yeah, once we finish today's lecture, I will just log in and try to download the PDFs and share them also on Moodle. All good. So now we're going to the object detection lecture. The object detection lecture is going to be a very long one. So we will be speaking a lot about the RCNN family, the fast RCNN and faster RCNN architecture. We will go in so much in depth. So now we're not going to be like the previous lecture where we skipped a little bit on things like superpixeling and stuff like that. Here, we're going to go into all the details that are needed, because object detection is, of course, a very important part of a data scientist's job or a machine learning engineer's job, especially in the applied world. So usually you would be either doing something like object detection, as we said, or something like pure data science for things like financial data or things like advertisements and stuff like that. So these are different locations where you could be interested in, or things like even spam detection and stuff like that. Also, even though it's natural language processing, but it does have a lot of basic data science embedded into it too. And then, of course, we will finalize the discussion by speaking a little bit about YOLO and how you can use, for example, things like Detectron to get started very quickly with your work. An honorable mention that I think you should at least take a look at RoboFlow. So RoboFlow is going to be a site that you will spend a lot of time on for both the project and for all the hooks that you will be doing. Later on, I will explain to you what RoboFlow does and how it does it. But overall, it's basically a website where you can annotate your own data. And this is something that all of you will be doing. You will annotate your own data, and allows you to basically get started with an actual model immediately. So let me just go to, for example, this data set. I did not annotate this data set, of course. But here, if you go to versions, export data, it can already tell you which version you want. So for example, YOLO v8, show the download code, all good. And here you can download that specific data set in the format that is perfect for YOLO v8. So YOLO v8, you can just run it immediately. And then if you want to actually get the code for YOLO v8, very simply, you come here, Colab notebook, done. So you're done already. You already have the code. It's going to load soon, one day. Yeah, here it is. All good, all good. And somewhere here, not here. A little bit, okay. Well, anywhere at the start, you just copy paste this code, copy it into Colab, you would have everything perfect. Run immediately the same thing that you are looking here, right here, and you will be able to have at least all of these results immediately done. So you will do absolutely zero coding, like literally zero. So all you have to do is just copy paste this code here, and zero coding done, you already have YOLO v8. If you want to do YOLO v7 or YOLO v5 or YOLO v6 or YOLO v there are hundreds of different YOLO versions. YOLO v4 is my favorite. This is the best one, or at least, well, it's one of the best ones. Immediately, faster RCNN, all of these, you can do them instantly. Just a click of a button here, and you have it. You trained your model instantly. So calculation is on Colab, 2 hours, you have your results. So here, it's very important for you now to learn how to do the annotation process. So as this course is, applied machine learning, your job will not be mainly to annotate, but your job will be for 100% to supervise annotators, right? The annotation process, you will have to supervise it. You will have to tell the people who annotate, I need this class, this class, this class. I need this class to be extremely precise. This class, I don't care about it. I need this tag, and this tag. I need these kinds of metadata to be extracted from each image. All of this information, you must be able to first do it by hand, you yourself, in order to supervise other people and see their results. And the good thing about RoboFlow also, it already tells you, for example, this is the benchmark results for your data. So it already builds a benchmark model, and this is the worst you should be able to do. So the worst you should be able to do on this data set is 92% MAPE. We will speak about what mean average precision is later on, but this is just the basic introduction to what this beautiful RoboFlow website can allow you to do, especially this part where you have access to all the models. You have semantic segmentation models, you have instance segmentation models, you have classification models, and 19 object detection models. You have things like, for example, if you want to do something that is based on, as we said, transformers, or you have visual attention. So here you have multiple transformer models, and you can immediately get started using them, as we said, with a click of a button, right? So it's zero work, absolutely zero work for you that needs to be done. Immediately get started, immediately get results. That's it now for RoboFlow. I think that was a promotion for their website, but it's a very beautiful website. I highly recommend using it and at least getting to know either RoboFlow or something similar to it. I also use Supervisely. It's pretty nice for things for when I have like a very gigantic amount of annotators that I need to manage. Usually Supervisely is a bit better for that, but when it comes to actually training, RoboFlow is usually the best, and convergent between different formats of the data set. So yeah, for today's lecture, we're going to speak about things like object detection using RCNN. This is the basic model for object detection, something that we will actually construct from scratch together. We're not going to look at its architecture and explain it. We are going to explain it, or we are going to build it together, right, from scratch. And then we will speak about fast RCNN and faster RCNN, which are improvements over the RCNN architecture. And then we'll speak about the YOLO architecture. So let's start with what is object detection, right? So for classification, it's a very simple task. You have an image, you attribute a category to that image. You attribute a class, a label to the globe, to this whole image, right? To the whole entirety of the image. There is a cat somewhere in this image. I don't care where the location is. I just care that there is a cat in this image. Now, for object detection, your job is no longer to just say there is a cat or there is a dog, or there are cats and dogs in the image, for example, for multi-labeling. But the job is to actually say where each cat is located, where each dog is located, and where each duck is located and of course, what their class is. So now you have two things to do, right? The first one is what are the categories of the objects here? And the second one is what is the location of them? How do we actually do it in real life? Very simply, we first find the objects and then we classify them, right? So we find potential locations of objects and then that shrinks into a smaller image. So here is the full image. You say that potentially there is something here, run a classifier, and it tells you, oh, you actually found a cat at this region, right? So this is a very simple way of doing this task. A quick question about this one, and we already answered it the first lecture of this course, but can somebody remind me, is object detection a classification task or a regression task?
Classification problem.
And so let me give you what the
Segmentation. Did you mean it?
Nuh-uh. Let me tell you what the actual results of the model will be, and then you will say. So it will be something like this. Cat, x coordinate equals 50. Y coordinate is equal to 50, for example, 2. The width is equal to 90, and the height is equal to 70. So this is a class, right? This is something that we will predict, which is a category. So this is a classification. But we will also be predicting other things, which are numbers, right? So object detection task is a merge between classification and regression. We will be performing both classification and regression at the same time. Yes, exactly. So since we are predicting numbers, it's clearly a regression. And since we are also predicting categories, it is clearly a classification. So object detection is both situations at the same time. Hopefully, during the next few lectures, we will also speak about segmentation. And in segmentation, you'll be surprised what it is, right? Is it a regression or a classification? And I think that answer will be quite of a surprise. But for now, for object detection, we are looking at it and we see that it is both a classification and a regression task. The actual examples of what, or application areas of what classification does, it's endless. You got self-driving cars, you got smart cities right now trying to do things like crowd control or doing things like better better traffic orientation. So for example, if you have multiple highways, you could be communicating with the people and just redirecting them instead of letting them go through the city, tell them, oh, this is better, things like this. So all of these things are based on the basic premise of being able to recognize objects in images. So here, for example, this is a simple example of counting the amount of vehicles that come inside the city from this highway and come outside of the city from this highway. This is, you know, as a simple project, it's not something extremely important, right? You're just counting vehicles. So it's very simple to do, very basic application, but the actual use case of this one is supposed to help basically the city organize its highways better, or organize the traffic inside the city better, organize things like, for example, parking spaces, improve everything about the city could be improved. Having just this simple information, of course, not on just one highway, but for every single highway outside, this could give you like an estimation of how many cars you have inside, and that could give you like an estimation of what the pollution is in the city or something like that, right? So here you see it tracks, it not just detects the car at a single location, but it tracks the car over the video. So we have multiple frames consecutively, and we're detecting the cars, but also maintaining. You see this car 32? We'll go with it through the whole route. Car 41, you see car 41, car 41, car 41, till the end. So it's not just basic object detection, it must include the concept of a video, right? So working with videos, majority of the cases, what you will be doing is you will treat the video as a sequence of images and apply object detection on these images, and then apply a simple algorithm that performs that tracking, right? So the tracking is actually a pretty simple thing to do once you have a good object detection algorithm. It's not very simple, right? But it does work, right? It does at least give you something. So here, this one, no, not perfect. It thought that this was a bus, this was a truck. So clearly this model is not perfect, but still it is useful enough for us to get started or to help the city make better decisions. Does the problem require machine learning? Amazing question. I really love this question, right? Remember when we were speaking about the first steps for you as an actual data scientist, not just somebody who's doing research where everything is machine learning. The question of does this require machine learning is very important question. And in this case, yes, it does, right? So yes, it does require a lot of non-machine learning things. So big servers that are taking this information and building some algorithms that will optimize the route. That part is obviously not going to be machine learning based. But this part, which is, the actual model, looking at the image, counting the fact that there was a car coming inside or there was a car going outside, this is definitely something that requires machine learning. You could try to do this using some sensors and everything else, but at the end of the day, it's best done using machine learning because you will have things like trucks, you have things like cars, you have things like those big trucks, which basically slow down traffic a lot. And having this information that there is a big influx of trucks coming into the city through this highway is an extremely important information to have. For example, the world's biggest traffic incidents that happened in China happened exactly because there was a very major amount of trucks go through the big highway, which basically slowed down the whole highway capacity and caused the biggest traffic in literally humanity, right? It lasted for multiple days where people were just basically there for multiple days. Nothing was moving, right? So just having this information that there is a big amount of trucks that is going into the highway, you could start immediately telling these trucks, stop, right? You could immediately bring in all of cops and they would tell, okay, trucks do not move right now, stay putted. We have lots of vehicles that are passing, and they could continue going after night, right? So applications of object detection in real life are endless. We have things like facial recognition and facial recognition. Of course, facial recognition is not part of object detection, but the detection of the human face on the images, this is something that is extremely important, and it is done with, of course, object detection. Parking lot monitoring is again something that is specific to, let's say, smart cities, where this allow you to understand the capacity of the parking lots around you. So, for example, something that could be embedded into Google Maps, it should be able to tell you if you're going to work, oh, use parking lot is that one because that one has only 2 free spots and might disappear, whereas the other one, it has like 10 free spots and they're probably going to disappear because it's low traffic. So again, amazing applications for object detection, and the job opportunities for experts in object detection are quite endless, right? So I think the biggest amount of job opportunities that you will find are definitely for data scientists, because that's where the most of money is located. And then you have applications for things like basic image classification, especially in big factories where they have like control of the whole situation, and they can put like the camera in specific locations with perfect lighting and everything else. So basic image classification is still extremely useful, especially inside big companies, especially factories where you will be needing. But when it comes to actual real life and something that is outside of the actual factory, something that you have absolutely zero control of, these situations you're going to need object detection. And such cases are, as we have seen, smart or self-driving cars, smart cities, things like projects like the NEOM project right now with that big smart city that they're building, and they are recruiting hundreds of machine learning engineers in the field of computing, especially for applications. So now we will go into the first actual model that we will see that actually performs object detection. And this basic model is quite simple, right? It will be a sliding 2D CNN. It slides through the image, and here, for example, starts at the top left position here. If here it applies the CNN, if it finds an object, it just says that there is an object at this location. If it doesn't, it moves to the next one and search here. So the search is very simple. You just send this small part of the image through the CNN, and the CNN will classify yes or no. And you will be doing this multiple times, and there you go. You found your object. One big problem that you're seeing already here, when you are using a forced sliding window, so something that is extremely specific, you're never going to find the best size for the object. What if the object was too big to fit inside this rectangle? For example, here in this case, some parts of the object are not inside the rectangle, and there's just no way that we will be able to find those parts using the sliding 2D CNN algorithm. So yes, it could be done like this, right? You see, it's a very simple technique and it works. It gives you results for specific situations, right? If you, for example, working as we seen earlier in the highway, you already know what the average size of a vehicle should be. So you should have an estimation of what is the size of this window, what should be the slide. Remember what is it called? What should be the stride, sorry. What should be the stride value, because you have some domain expertise. But this is definitely not a model that you could just use anywhere out there, right? And again, there is a big issue. Can somebody tell me what this big issue is? Applying a CNN multiple times, let's say 20 to speed. Yes, speed, exactly. So the speed is exactly a very horrible thing about this model. And for us, as we have seen, we have like real-time feed video that is coming into the model. So we can't spend, I don't know, 10 seconds for each image. So that's definitely impossible. We need something that is much faster. An improvement of speed could be like this. You have this image pyramid technique. This image pyramid technique is extremely important, especially if you will someday maybe study the course of Introduction to Computer Vision, or I think it's called something like Computer Vision, Traditional Cases, something like that. So it's a course in Innopolis, and you will see these applications of things like this. So basically you have a pyramid of images, and especially in old cases, how was this useful? And it's still till now, it's a very important technique of having this pyramid of images like this. But the idea is very simple. You basically start with the whole image like this. And instead of going through this whole big image like, I don't know, 100 times, you would just go through it 4 times and find a potential region in this image that is actually could be an object. Then, so in this place, you search, let's say 4 times at this size. You go back to a bigger size now. And in this region, you're not going to search here. You don't need to search here. There is nothing. You don't need to search here. There is nothing. You don't need to search here. There is nothing. Only search in these places with potential objects. So instead of searching in this region, I don't know, 100 times, you will be searching only 4 times and making the size even smaller and make the image bigger again. And instead of searching in this whole area, which is a lot of work being done, you will be only searching in this region and improving the location for object. And let's say you will do that 4 times. Here again, you will do the same thing 4 times and 4 times. You sum this whole thing, it's like 20 passes through the CNN instead of, I don't know, 400 by 400, which is like, I don't know, a very, very large number of applications to get the same performances. So this could be like a very good improvement of the speed for an object detection model. This idea, as I said, it's definitely not the best in this case. It does improve the speed a little bit, and I chose to keep it, especially for those who will continue in the field of computer vision, and especially will study the traditional side of computer vision with these kinds of pyramids are extremely useful. And of course, even for future types of models, even for classification, there are some very important models that does this pyramid technique, and it's very good. Next thought is something I'm not sure, but I think it was Polina that asked about it. Who was the person during the last lecture who asked about superpixeling? So who asked about superpixeling last time? Nice. Good question, Polina. So remember with superpixeling what we were doing? Let's go back here. With superpixeling, what we were doing is a very simple thing. We would just look at the pixels that are close together. If they are similar, we group them into a region. Can we do the same thing, but instead of calling it a region, we will call it a potential object location, right? So for example, if we start here with the blue, it will group all of this big sky together, and there you go, a potential location of an object. It comes here to this truck, and it will find that these pixels, the red pixels, they look similar, and it would say that this could be a region for a potential object. It goes back here, looks at these pixels, they look similar, groups them all together, and it might say, well, this could be a potential object. So this is a technique that looks at the pixel values and combines them together in what we call, instead of calling them regions in the last time, now we will call them potential objects. Later, we will have a more technical name for these potential objects, but for now, let's just call them a potential object. Now that we have this red part as a potential object and this big white part in the back as a potential object, can we merge different parts and create another potential object? Absolutely. So the algorithm that we will be using right now, which is called selective search, it does exactly what I just described. It first looks at the pixel sizes and pixel values, which are close together, clusters them together, and then on those clusters, it will create new potential objects by combining different cluster locations. How does it do exactly that? Let's go to a beautiful link. Selective search. Not this company. No. Okay, this is good. And understanding selective search. Yep. Let's share the screen again. And this is what basically it does. It's a greedy algorithm that calculates the similarities based on pixel values and color similarities. So the difference in the color value, texture similarities. So it does have a way of calculating a texture value, and it calculates that very simply through textural similarity are calculated using generated 8 Gaussian derivatives of the image. So for those who are going to study the computer vision course, you will see how can you use Gaussian derivatives in order to calculate things that are extremely important for classification. So extracting features in general and extracting features like this, for example, for texture, especially for something like bag of visual words model that you will, as I said, you will definitely study in the computer vision course. Size similarities. If the two objects or the two clusters are similar in size, we might choose to merge them together. Fill similarity. There are different, so these are all heuristics that basically allow us to get different potential regions or potential objects around the image, right? And here you can see two different implementations of it. Selective search is a very simple model or a very simple algorithm. It's a greedy algorithm. I'm sure you have done greedy algorithms together, but in not computer vision courses. I mean, in basic data science, in basic data and algorithms structures, data structures and algorithm courses. So greedy algorithm, it's a very simple one. As we said, it just combines different pixels together based on their intensities, on their texture, on the color value, Others, they use information such as the lightning. Everything is being used as a heuristic to combine different regions. Once we combine those different regions, what we do is we propose even more objects by combining regions together or combining potential objects together. So as we said, we will combine the red forest. We will merge all these red pixels together, and then we will merge the white pixels in the back together. And then we will say, what if this red part and this white part are part of the same object? So we propose a new location. This one, sadly, as you can imagine, it proposed lots of combinations and lots of objects. So it usually gives you around 2,000 combinations of objects. But the good thing about it is it's much better than the sliding over the image. So it's a bit better. So it's a lot faster. It provides better results, more optimized results, more how do you say this? More personalized results, right? But still, 2,000 potential objects is a lot of objects to go through. For each one of these 2,000 images, we will send them through the CNN. So you can imagine this is something that usually takes around 40 to 50 seconds to do for a single image. So single image object detection takes around 50 seconds. Definitely not something that we can afford to do for our use cases that we have seen earlier. And this is why there are, of course, much better models with better ideas. So now let's go from selective search to the next step. How can we know if our model's performances are actually good or not? Right. So we have something, for example, for classification, you have accuracy. For regression, you have, what do you have for regression? Come on, give me names. How do you evaluate a regression model? MSE, RMSE, MAE, R squared. Very nice, Karim. Thank you so much. So yeah, you have different metrics to evaluate different types of models. For classification, you have precision, recall, accuracy, F1 score, etc. For regression, you have R squared, you have mean squared error. Yeah, mean squared error. You have mean absolute error. You have multiple types of errors that you could use to basically perform or estimate the performance of your model. But for object detection, we have one extremely important metric. Of course, we will have other metrics that are built on top of it. So we have something that is like a combination of intersection over unions over time. But this one is the most core metric for evaluating a object detection model. What it simply does is, this is, let's say, the prediction. This is your prediction. This is what the model has predicted. And this is what the actual object is located in. So this is the annotation. This is the real location in the data. So clearly we see that it's not perfect. How can we put this? Well, it's not perfect, but it's okay. How can we put it in words? We put it in the following number: intersection over union. So we put the intersection in here, divided by the union of the prediction and the actual location of the object. And this gives us a single value between 0 and 1. So 0 means your model is absolute garbage. 1 means your model is absolute perfection. And you should aim for something that is bigger than 60. If it's bigger than 60% or 0.6, it's good. It's better than nothing. Okay? So does the idea of intersection over union seem logical as an estimation? Seems good? Okay, yes. Perfect. So now, before we actually get into the first algorithm that we will be studying for actual object detection, we will first speak about non-maximum suppression. So non-maximum suppression is a technique that is extremely used in the field of computer vision till today, and it allows us to basically, any model that you will see outside, this is something that must be a part of it, right? So even YOLO V8, which came out, I think, like a month or so ago, it still uses non-maximum suppression. So this is a technique that is extremely useful for all object detection models. And what it simply does is, when your model proposes the following, right? So let's say with selective search, there were 3 object locations here, sorry. So selective search proposed these 3 regions, and your classifier has predicted that there is an object in these 3 places. All of these 3 objects, if you count them 3 times, it's going to be scary for your model, right? The model is going to be, or for your service, the server is going to be, oh, we have 1 billion cars coming in because you keep counting the same car multiple times, which is not good. So we need a technique that allows us to go from multiple predictions for the same object into a single prediction for a single object. So can somebody give me an algorithm that can do that? This is something that is completely algorithmic. So let's say that this one had a prediction of 0.6. This one had a prediction of 0.99, and this one was predicted with a probability score of 0.6 also. Which one do we want to keep? Amazing, thank you so much, Polina. So we want to keep the 0.99, and everything else that is merged with it, we remove it. So if we do this exact as we just said, right? So let's imagine that there is an object here and it is good and it's a perfect object with also 0.8. This is good, we want to keep it. If we keep only the highest score, we will remove this object too, which is not good. We only want to remove duplicates of the same object. Now, how can we find duplicates of the same object? Using the concept of intersection over union. Remember the concept of intersection over union? Go ahead. I need somebody to give me an algorithm. Who can do it? If you do it, you will get a bonus point. 1 bonus point in the final exam.
Okay, so okay, we take the value, the maximum value, and divide it by the all our other values. Okay.
Yes. So with intersection over union, we find all the other potential.
Another word, we get a percentage choosing our maximum value. Yeah.
So we should have a threshold, right?
Yeah.
So it should not be 0 and it should not be 1. So something like 0.5, let's say. If the intersection over union is above 0.5, we remove it. And then what do you do? Continue, you're at the right space. You just need one more step. Just, huh? Come on, Georgie, come on. You can do it.
Okay. Sorry.
What is the final one? Just, yeah.
Okay, we go. Okay, we have some threshold. We are going. Yeah, we take all values and take all more than 0.5.
Yep.
Yeah, and repeat for other object. Yeah, sure.
Perfect. Yeah.
And you write it. Yes. Okay.
Okay, so both Georgie and let's see who else did it.
A little bit confusing. Okay, sorry.
So we got Polina also got a bonus point. We got Georgie who got a bonus point. And let's see what Anwar said. Take pairwise IOU and combine those that intersect a lot and count them as one object. But which object do you take, Anwar? So when you combine them, which one of them do you choose? Which ones do you delete and which ones do you choose?
So we'll have several like rectangles that intersect. So we can
Yes.
take the rectangle that intersects
The
that
most.
like maybe combines IOU with others will be the most.
Okay, this is a great, yeah, you take the one that is hopefully the median location, right? The one in the center. Amazing answer too. For us, what we will be doing is we will take the highest prediction score, but your idea is absolutely also valid. So now we have 3 people who got a bonus point. So we got Georgie, Polina, and Anwar. Thank you guys so much and congratulations. So let's go. Let's actually see the steps of non-maximum suppression. So these are the steps of non-maximum suppression, as your friends, both Polina and Giorgio have described pretty well. Also, Anwar has proposed a different algorithm, but it works also as well. So this is what we call greedy non-maximum suppression. This is the most famous version of the non-maximum suppression. But if you go into your model, and hopefully in the future you will start, you know, how to say, fine-tuning these models, not just using default values by default for all of your databases. When you actually go into production, sometimes you will have to make improvements on non-maximum suppression. You will have to make improvements for specific anchor sizes and stuff like that. But for now, greedy non-maximum suppression is the one that we will be talking about. For, of course, in industrial settings, always try to find a better algorithm than greedy non-maximum suppression. There already existed. So let's just go, for example, and take a look at what we have already for something like YOLO v4 non-maximum suppression algorithms. Selecting the right for, yeah, the right bounding box. Okay. Yep. So they use something called bounding box suppression via non-maximum suppression, MITS. I don't know. Let's go to the actual YOLO v4 code. So this we will do it a lot during the lab part of this course, but let's go with, yeah, YOLO v4 darknet. Here it is. Let's go in. Let's go to the configs. So we will see these configs very well in the lab. This is going to be like the only part of the lab that is actually important. Let's go to YOLO v4 small one. Let's go YOLO v4 tiny. Can you see it? Here's YOLO v4 tiny. Yep. And here, yeah. So here, non-maximum suppression kind is equal to greedy non-maximum suppression. This is the actual algorithm that we will be using for non-maximum suppression, but it does support multiple versions of non-maximum suppression. So you could just go see the options for non-maximum suppression H YOLO layer, and it will allow you to just basically choose the one that is most optimal for your specific data set. But for the greedy non-maximum suppression that we will be studying here, it's very simple. Select the proposal with the highest confidence score. So we go to that 0.99. Remove it from B. B is basically the list of potential objects that the model has proposed. And add it to what we call the final proposal list. Let's name it D. So D right now has only one value, which is the object which has the highest score. Compare this proposal with all the proposals. Calculate intersection over union. If the intersection over union is greater than n, remove that proposal completely. That means it's a duplicate. So we find duplicate and we remove again. Now we do the same thing again. Calculate proposal highest confidence score that remains in B. So now we have fixed one object. Now let's go to the next object and repeat and repeat and repeat. So this is it, just 3 basic steps to get repeated, and you have your greedy non-maximum suppression. Here we will find the last part of today's lecture. So we will do this one and we will call it a day. And the next lecture, we will finish the RCNN family completely. So the RCNN family tree is basically the biggest family tree in the object detection field, mainly because it has brought the biggest innovation in the field. And then now, of course, we have YOLO, which is now a lot faster and it performs even better, sadly, than the whole RCNN family. But the innovation part of it is extremely low. So you will be able to understand it very well once you understand the RCNN family. So the RCNN algorithm is exactly what we have been describing so far. You take an input image, extract region proposals. So now we call them region proposals, around 2000 region proposal, using which algorithm? What is the name again? Selective search. So we will be using selective search in here. After selective search, we, what is it called? We force all the proposals of selective search to be in the same shape. So we just resize the proposals. So here, for example, it proposed this long person. We resize it into the same thing. If it proposed the hat, we will also resize it into the same size. So this is exactly extremely important, mainly because the CNN that we will be using here basically has no ability of handling images of different sizes. So as you can imagine, we must resize every single region proposal into the same shape, right? So here the problem is we will be applying the CNN 2000 times, which is a lot, very slow. As you can, even on the best GPUs, it will be an extremely slow process. So this is the problem of RCNN. So RCNN, this is the algorithm. We have seen this algorithm in detail, mainly because we studied individual parts of it before we looked at the architecture. But basically, this is what the problems of RCNN are. Training time is extremely slow. You have 2000 classifications per the same image. And in some data sets, you have like 2 million images. So 2 million times 2000 times, I don't know, let's say at least 100 epochs. So yeah, 100 epochs, yep. So you will have 2 million times 2000 times 100. That's just extremely impossible to do if you have a small, small amount of calculations. This is something that is definitely only doable by somebody like Facebook or somebody like Microsoft and Google. The other problem is the inference time takes around 47 seconds or 50 seconds, which is, as we said, a lot of time, mainly because for each image, you will perform a classification for 2000 times. So the object detection task, object detection is equal to 2000 image classification. Not good, not easy, not an easy thing to do. And the final issue is selective search algorithm is not data set specific, right? So it's just a greedy algorithm that combines pixels based on their pixel values. This works very well for photos or photographs. But if you are working, for example, with an artistic manuscript, something that is from Picasso or something like that, then this algorithm is not going to perform very well. Selective search algorithm is not going to perform very well. If you are working, for example, with the medical field, right? In the medical field, you have images which are usually grayscale, and you have like the MRI scans. Some MRI scans, they handle or they focus a lot on the muscle tissues. So you will have a different, grayscale image for the grayscale pixel value for tissues compared to, for example, something like the fats and the bones. And the differences like that in these kinds of situations, selective search as it is going to be unable to actually give you good results for your specific data sets. So here we have two issues or three issues: training time crazy high, inference time crazy high, and selective search is not data set specific. So these are the issues that we will need to fix in the following, hopefully in the following weekend. In this weekend, we will speak about fast RCNN and how they reduced drastically the training and inference time. And then we will speak about faster RCNN, which even made it, as we said, it made it even faster than that and fixed the problems of selective search. And hopefully we will also discuss Detectron and YOLO v3, and of course YOLO v4, YOLO v5, 6, 7, 8. We will discuss them during the lab part of this lecture. So do you have any questions about the left side? would it be easier from the model point of view to segment the whole image and then rectify the masks? The data set is harder to gather though. So with segmentation, I'm assuming you are speaking about semantic segmentation of the whole image, which is basically just a classification at the individual pixel level. Sadly, for segmentation, it takes a lot more data to provide a good segmentation model. But it's a good proposal, but there's one problem with also segmentation is, for example, if you have a cat, let's do the following. So it's a very good, definitely answer such as what the difference between semantic segmentation and instance segmentation. But sadly, semantic segmentation, which I'm assuming you are speaking about, will not work in the case, for example, you have a cat here and another cat in here. Your semantic segmentation will merge all of these because they are cats together, right? So we'll propose all of these as the same object. All of them will be thought of as the same object. And here it will be an object of category or of category cat. But when you go and try, as you said, to rectify these segmentations and make it just like this, a rectangle, you will find have a lot, and you will be proposing multiple instances of the same class together. So for example, if you are in a highway and cars are following each other, you'll see that you are using just one car, one gigantic car from the start of the way to the end. That basically defines the logic of doing object detection. So even for segmentation later on, we will see that the actual good model that we will be using is into two steps. First is detection and then segmentation, right? So object detection is extremely important to allow us to differentiate between different instances of the same category. But definitely it is extremely doable if you have this information that you will not have multiple instances of the same class in the same image. So if you have a specific situation, absolutely what you propose would be amazing for that specific case. Thank you so much, Kareem. Anybody has some questions, maybe? Oh, good. So I think we could take like the rest of the lecture as like as a rest. So yeah, we will meet Sunday, I think, right? So we will meet this Sunday and we will finish this lecture. As you can see, the rest of the steps are going to be extremely based, so they're going to be a little bit heavy. This is why I will be able to actually explain this on a brain that has been accumulating information for. The rest of this lecture is definitely going to be extremely architecture heavy. And we will go to all the details needed for this lecture because it's extremely important. The same non-topic related question. What about real-time speech recognition? Is there ways to do it? Streaming data or another formulation to detect voice and words. Sadly, you can't do it, of course, real time, because when I am speaking, I did not finish the word speaking. When I was speaking the word speaking, it can like the speed, let's say at instance time is equal to 1, I just said speed, and time is equal to 2, I said yeah. So definitely it's not going to be something that is extremely real time. You have to do it real time unless you have extreme mechanisms of correction. So basically you try to guess what the word is going to be and build another model that's going to fix the proposals along the way and make sure that the sentence has semantic information in it. But there are hundreds of different algorithms that can provide with my real-time speech detection or speech recognition. So it will be like at least 2 seconds late than the actual word being announced fully, but that's not horrible. It's not super bad. So for example, if you speak with Siri, even still be, reading a little bit, and then we'll finish the sentence, right? So closest we can get so far to what we call as like real speech recognition. That's the best we can do so far. As we said, there are hundreds of different algorithms that can do this. Some of them are extremely big that, of course, we cannot experiment with, and some of them are actually small. You could get some results. It depends on what language you're working with. So, for example, for English, a lot of them which exist already, which are already pre-trained, and a lot of data sets already exist that can help you actually get started with this. But for example, for Russian, I had a couple of students who did this, multiple students actually, as a task for their project, and for a little bit finding data sets for like Russian speech recognition, and we trained for such tasks. And if you're working with Arabic or with language like that, then it's even harder to actually do. Perfect. If you guys don't have any, okay. If you don't have any questions, then we meet hopefully on the next week, and we will be discussing the rest of the object detection lecture. And by today, I will be sending you the first. As we say, assignment is not timed, so you can do it anytime you want, but preferably do it this week. That by the end of the course, you will have to focus on your project, because the project is going to be extremely time consuming. Have enough time on the home, so start as early as possible, but no pressure if you cannot. Thank you guys so much, and have a great rest of your day and the week.
Bye.
Bye.
Bye. Thank you.